Hi, I'm Ms Hearn. Let's get started.
This video is about compound linear inequalities, but it's not about solving for x. This is about the last couple of steps after you already have isolated x. Here are the three types of solution sets that we will see in these types of problems. So one type is in OR problems, where you see something like x is less than -1 or x is greater than or equal to 3. Another type is the AND, where you see something like x is greater than -1 and x is less than or equal to 3. And then the last is between. It's really an unwritten AND statement. We don't have to actually write the word AND because it's implied, and it looks like -1 is less than x, which is less than or equal to 3. You could also read that as -1 is less than x and x is less than or equal to 3, but we just haven't written the AND. In understanding how these different types work, it helps to look at a graph. OR statements include numbers that satisfy either condition. So in the case of x is less than -1 or x is greater than or equal to 3, we're going to look at including numbers to the left of -1, but we also are going to include numbers that are to the right of 3. We also have to pay special attention to our boundary points, -1 and 3. -1 is not included in our solution set because there's no equal to. So we use a parenthesis facing the shaded area to indicate that. 3 is included, so we're going to use a bracket facing that shaded area. Now let's talk about the AND statement. Again, graphing helps. So I'm going to draw a number line and I'm going to include my boundary points, -1 and 3. An AND statement dictates that both parts have to be true. If either one of the two inequalities is not satisfied, we have to throw out the number. But when we look at our number line, think of it as being divided into 3 segments, and we have to think about whether or not each segment satisfies both of the conditions. For example, on the left of -1, we're going to have to throw out that segment because numbers to the left of -1 are definitely not greater than -1. While they might be less than 3, they still don't satisfy the x greater than -1 condition, so we have to throw them out. We also have to throw out things to the right of 3 because those numbers like 4, 5, and 6 are definitely not less than or equal to 3. They make the x less than or equal to 3 statement false. We have to throw out the two ends of the number line. And we're left with the region in the middle. All of those numbers satisfy both of the conditions. For example, 0 is greater than -1 and 0 is less than or equal to 3. Then we have to label the boundary points, decide whether we're including them or not. In this case, -1 is not included, so we use parentheses, and 3 is included because we have an or equal to, so we use a bracket. The between situation. Notice that what this is saying, -1 is less than x is less than or equal to 3, is really that x is between -1 and 3, which is exactly the same graph that we just saw. The only thing we have to be careful about here is that we pay attention to the inequality symbols. Both of the inequality symbols have to face the same direction in order for the statement to make sense. And if you were to take out the x from the statement, it still must make sense. In other words, -1 in this case has to be less than 3. We couldn't have an inequality facing the other direction. Let's talk about how we write OR statements in interval notation. So one thing that's important to understand is that OR statements almost always include an infinity symbol. So in this example, we're going to write the compound inequality x less than 1 or x greater than or equal to 4 in interval notation. So again, we've already solved our inequality. We've isolated the x. Now we just have to write our answer in interval notation. And I find it's helpful when you're first getting used to interval notation to always graph first. So step 1 is going to be to draw a number line with your boundary points. That looks like this in this case. Always make sure that your values are in numerical order from left to right. So 1 is to the left of 4. Now we want to shade the regions that make the statement true. So we want to shade the region to the left of 1. And we want to shade the region to the right of 4. Remember, or includes everything. Anything that makes either of the statements true. Then we want to label our boundary points, mark them off with parentheses or brackets, depending on if we have an equal to. We do not have an equal to for the 1, so that's going to be a parenthesis. We do have an equal to for the 4, so that is going to be a bracket. So here is our graph of the inequality, and we're going to translate it directly into interval notation. We're going to list the ends of the shaded intervals in order from left to right and put a U in between them. That U represents the word union, uniting the two sets together. Keep in mind that left arrows are always denoted by parenthesis negative infinity, and right arrows are always denoted by infinity parenthesis. So on the left arrow, we write parenthesis negative infinity. Then we write the boundary point 1 with a parenthesis just like it appears on the graph. That's the first shaded region. The second shaded region starts at 4 with a bracket, and it goes to the right arrow, which is always infinity parenthesis. Now we join the two intervals together, we unite them with a U for union. Union always means or. Now let's talk about interval notation for and. And statements can always be simplified to one interval or the empty set. For example, if you're asked to write the compound inequality in interval notation and you're given x is greater than -1 and x is less than or equal to 1/2, we're going to start out by graphing the boundary points again. So make sure -1 is to the left of 1/2 because it's smaller. Now remember, and statements only include those intervals that make both statements true. So we want to eliminate any regions that make either part false and shade the rest. In this case, we're going to eliminate anything less than -1 because it makes the first inequality false, and anything to the right of 1/2 because it makes the second inequality false. We're going to discard those, and what's left is what we shade. Then we're going to put parentheses or brackets on our boundary points. Remember, parenthesis means that we don't have an or equal to in the inequality, like at -1, and bracket means that we do, like at 1/2. Finally, we take the graph and translate it into interval notation by listing the ends of the shaded interval from left to right. On the left, we have -1 with parentheses, and on the right, we have 1/2 with a bracket. And that's our interval. Now let's talk about interval notation for between. The first thing you should know is between statements are always one interval. So for example, if we were asked to write the compound inequality -1 is less than x is less than or equal to 1/2 in interval notation, well, the first thing we would do is make sure that we didn't make a mistake up to this point. We want to make sure that the inequality makes sense. Well, first check that the inequality symbols are facing in the same direction, because if they're not, then a mistake has been made. The next thing you want to check is that if you were to remove the x and either of the inequality symbols, would the statement still make sense? For example, in this case, we'd be left with -1 is less than 1/2, which is true. So it would still make sense. After that, we're going to use pretty much the same steps we did before. We're going to draw a number line graphing the boundary points, making sure to put them in order from left to right. And then in a between, since x is between -1 and 1/2, we don't even have to really put much thought into it. We know we're going to shade the segment in the middle. Then we use the same rule as before. On our boundary points, we're going to use parenthesis if there's no equal sign, and we're going to use bracket if there is an equal sign. In this case, -1 is strictly less than x, so it's parenthesis, but 1/2 could be equal to x, so we have a bracket. Finally, we use that to translate directly into interval notation, meaning that the endpoints of our graph become the endpoints of our interval. And there's our interval. But there are a couple of special cases that come up in interval notation. Let's take a look at those. First compound inequality we have here appears to be a between statement. Remember that we always want to check that the inequality symbols are facing in the same direction, and they are. But the next thing that we need to check is whether it would make sense if I removed the x from the inequality. So would it make sense to say -2 is greater than 1? And the answer to that is no. At some point, an error was made It is never the case that -2 is greater than 1. So if you were solving a problem and you got to this point, probably you made a mistake. Now, if you were given this problem directly, then the answer would be, if you just say that this is the empty set. There's no x that's between -2 and 1. That doesn't make sense. So when a between statement does not make sense, there is no solution. Now let's look at the next situation. It's an and statement. We have x greater than or equal to 1 and x less than -2. Since it's an and statement, I'm going to mark off my boundary points. Notice that -2 is actually to the left of 1. You've got to make sure to put those in the proper numerical order from left to right. And then remember that when we have an and, we need to think about which intervals make one of the statements false, because we got to discard those intervals. So in this case, let's think about x greater than or equal to 1 means we only want numbers to the right of 1. We have to discard anything to the left. On the other hand, x less than -2, that means that we need to discard anything that's not less than -2, that's to the right of -2. So again, we're going to discard the numbers between -2 and 1, but also the numbers greater than 1. Here we see that we're left with nothing. And there is no number x that is both simultaneously greater than or equal to 1 and less than -2. The interval notation is empty set. You may also see it written in set builder notation with just the set symbols and nothing inside. So this next example looks very similar to the and question, but it's an or, and the inequalities are switched around a bit. First of all, when we have an or, we're looking for what makes the statement true. Anything that makes either part of the statement true is going to be included in one big set. In this case, we're going to still mark off our boundary points, which happen to be the same two numbers. And we're going to look for what makes either one of these statements true, and that's what we're going to shade in this time. X less than or equal to 1. Well, that would be everything to the left of 1. Since it's or equal to, we're going to include the 1 in that set, so we have a bracket. X greater than -2. Well, there's an overlap. This is actually parenthesis. We're not including -2. Okay, and so what happens when we put two overlapping sets together? Well, we get the entire number line. So the left arrow is represented with -infinity and a parenthesis. The right arrow is represented with infinity and a parenthesis. So in interval notation, this is -infinity to infinity. And sometimes people would read this as all real numbers. So these are some of the special cases that can come up. This concludes the video on writing solution sets to linear compound inequalities in interval notation. I hope you find it helpful.